Hello, this is Jenna Nichols. Today we're going to talk about structure 1.3.7. This is higher level only. And we're going to look at successive ionization energy data and how that tells us a little bit about the electron configurations for atoms. So a quick reminder about ionization energy if we're looking at a Bohr model. And let's say we have, well, let's do magnesium. So magnesium has 12 electrons, and so it has 2 valence electrons. So if I'm talking about the first ionization energy, it's the energy required to remove one of the valence electrons. The second ionization energy would be the other valence electron. And the second ionization energy will be a little bit higher than the first ionization energy because of the charge difference when you're comparing the protons, the 12 protons in the nucleus compared with the number of electrons now. When you go into the third ionization energy, though, you're going to start taking a core electron. And so the effects of just charge are much less when you're comparing it to the difference in distance. So those electrons are much closer to the nucleus and will take much more energy to remove and break those forces. Don't forget that ionization energies are positive because it requires energy to break forces of attraction. So it is endothermic for ionization energy. So that brings us to successive ionization energy. That's where we're comparing the first electron to be removed to the second, to the third, to the fourth, to the fifth, etc. So succession. The first electron for sodium is the valence electron. But then after that, we have to remove core electrons. So the second electron to be removed will be from the second energy level instead. And then the third electron to be removed will also be from the second energy level, fourth, fifth, etc. So there is a large gap in ionization energy between sodium's first electron and its second electron because the second electron to be removed is much, much, much closer to the nucleus. So that distance between the electron and the nucleus is much closer for the second energy level compared to the third energy level. Now for magnesium, because it has 2 valence electrons, the first one to be removed will be a valence electron, and the second one to be removed will also be a valence electron. The third electron to be removed will be from a core electron from the second energy level. So the third one will take a lot more energy than the first or second. And so you'll see like a really, really large gap in ionization energies between the second and third electron to be removed. So that can start to tell us something about the electron configuration of these atoms. You can find gaps, large jumps in ionization energy from one electron to the next. And that can tell us where they are moving significantly closer to the nucleus. So wherever you see the jump, you're going from valence shell to a much closer energy level to the nucleus. Now let's look at those orbital diagrams. So 1s, 2s, 2p, 3s. Sodium has 11 electrons, like this. And magnesium has 12 electrons. One, two, okay, so if we're looking at ionization energy from this perspective, the highest energy electron will be the 3s for sodium. That's the first one to be removed. Let's see if I can do this a little better. So the first electron to be removed versus the second electron to be removed, that will be, there'll be a very big difference between the first ionization energy and the second ionization energy. So you'll see a big difference there. This would be the third electron to be removed, fourth, fifth, sixth, seventh, and then eighth. You will see a bit of a difference between the seventh and eighth compared to like the sixth and seventh, just because of the difference in sublevel. But you'll see a much more marked difference between complete energy levels. And so if you're looking at then for magnesium, this would be the first electron to be removed, second, and then third. So if you're looking at its ionization energies, the first electron, first ionization energy, second ionization energy, third ionization energy, very large gap between those two. Let's talk about elements that are isoelectronic. So fluorine's orbital diagram up at the top here, it has 9 electrons normally. Fluorine, when it forms ions, will gain an electron to fill up that 2p sublevel. So it will gain an electron in this last spot and then become fluoride. And it will have an electron configuration that is the same as neon. So it's isoelectronic with neon. Sodium, on the other hand, has 11 electrons normally. When it forms an ion, it wants to lose its outermost valence electron. So when it loses that electron and becomes positive, you're going to see this outermost electron go away. So you won't have this 3s orbital anymore. And that leaves it isoelectronic with neon. So when you have these 3 species present, so fluoride, F negative, neon, and sodium ions, same electron configuration. They will not have the same ionization energies, even though they have the same electron configuration, and it's because of their protons. You have 9 protons in fluorine, 10 protons in neon, and 11 protons in sodium ions. And those don't change when you form ions. Remember, the protons are not gained or lost when you form an ion. So fluoride of this set, fluoride will have the lowest first ionization energy because it has the least protons. So this one will be the lowest first ionization energy. Neon's in the middle, and sodium will have the highest ionization energy of the 3. Because it has the most protons, it's hanging onto them the tightest. So that's how you would compare a set of isoelectronic species, is you have to look at the electrons, but more importantly, we're looking at the protons. So this is a really good section to work on one of the tools for chemistry, that being databases. So you'll be able to look these up for free in particular databases. I used webelements.com, so to see the link here, it's completely free, and you can find the ionization energies for different elements. And you'll find these successive ionization energies. So I pulled chlorine here just to see. Chlorine has 17 electrons, and 7 of those are valence electrons. So if we look at chlorine, we see our enthalpy values, and that's just a way of measuring ionization energy. You'll see it gets higher and higher, slowly. Yeah, it's like 1 to 2,000 for each of these. When you get between the 7th and 8th, it goes up by like 20,000. So that is because you're going from the 3rd energy level to the 2nd energy level. And the 2nd energy level is so much closer to the nucleus that suddenly that 8th electron is going to take so much more energy to remove because it's much, much closer to the nucleus. So we can see these values supporting the evidence for the energy levels and how the electrons are arranged. Okay, so here's another example. We've got the first 4 ionization energies for an element. So the first energy is 738, the second one is 1450, the third is 7730, and the fourth is 10,550. So what group is it located in on the periodic table? You want to look for the jump. So the difference between first and second is about 700. The difference between the second and the third is about 6,000. And the difference between the third and the fourth is like 3,000. So the largest gap is between the second and third. That means the first two electrons to be removed are valence electrons, and the third one is a core electron. So I don't know how many total, but I know two of them are outer, and the third one be much closer. So it could be beryllium, could be magnesium, but you're looking for something where there's only two valence electrons, which means it's in group 2. Okay, so now let's link this kind of forward to a discussion about transition metals and their different oxidation states. Remember, if you haven't quite gotten to this in your curriculum, we will get there, but this is nice if you've taken a prior chemistry course, you can kind of link the information together. So patterns of successive ionization energies of transition elements, they do help to explain the variable oxidation states. If we look, I pulled this again from webelements.com. This is for iron, which is a transition metal. Iron tends to form +2 and +3 ions. And if you'll notice, these first few ionization energies they're all relatively low comparatively. But the difference between that second and third ionization energy is pretty small for a second and a third ionization energy. So the difference in energy there can help us explain why iron is likely to form a +2 by removing 2 electrons, or a +3 by forming 3 electrons, because it doesn't take that much more energy to remove a third one. And that's true for other transition metals as well. And it all has to do with the difference in energy, especially when you're looking at like 4s versus 3d. That's most of the time where you're going to see these kinds of applications in IB chemistry.